Okay, we're going to look at chapter 5. This is where we're going to draw structures and look at shapes. So first we're going to talk about what kind of bonds we have. So there's a couple different bonding theories. These theories show how and why atoms attach to each other. We can look at the geometry or the shapes of our molecules, and this can help us predict physical and chemical properties. The Lewis bonding theory is what we're going to focus on along with the VSEPR theory. The Lewis theory is one of the simplest bonding theory, and this is all pretty much based on our valence electrons. So understanding how many valence electrons each atom has is super important. Why do atoms bond? Well, we've learned that they bond in different ways. They bond by either sharing electrons, or they lose electrons and gain electrons to form some sort of chemical bond. The reason this happens is because, generally speaking, when the bond forms, whatever kind of bond it is, it's lower in energy than without the bond. So everything in chemistry wants to go to a more stable state. So when we form a chemical bond, the potential energy of those bonded atoms is less than if they were separate. So it lowers the energy when we make some type of bond. Our types of bonds, again, are an ionic bond, which is between a metal and a nonmetal, a covalent bond, which is between two nonmetals, or a metallic bond, which is two metals put together. We are actually not going to focus at all on metallic bonds. We're just going to keep with the ionic and the covalent. So remembering the ionic bond, you have a cation and anion that come together because of a transfer of electrons. That could also include a polyatomic ion. And then your covalent bonds is when we share electrons. When we have a bond that forms, that bond has what we call some level of polarity. Polarity is how they share the pair of electrons between the bond. Now remember, if we form a single bond, they're sharing one pair of electrons. If we form a double bond, they're sharing two pair of electrons. Triple bond, they're sharing three pair of electrons. Polarity is focused on how they share those electrons. And what I mean by that, it's as simple as this. Do they share, if you have two atoms that are sharing electrons, do they share those electrons equally? Or does one of them have more pull on them than the other? And I'll show you what I mean by that. So we're going to focus with polarity mostly on covalent bonding. We have what we call, so again, a covalent bond is between two nonmetals, and it's sharing one, two, or three pairs of electrons. Now we have two types of covalent bonds. We have what's called a polar covalent bond and a non-polar covalent bond. A polar covalent bond is when two atoms share their electrons unequally. Okay, so what I mean by that is, if I have, I'm going to show two sharing a pair. If I have chlorine, oops, sorry about that. If I have, we know that chlorine exists in nature as Cl2. So it's two chlorines that are held together with, with a single covalent bond. Sorry about that drawing. But anyway, that single covalent bond is a pair of electrons in between those two chlorines. These two share that pair of electrons equally because they're the same atom. If I were to have, let's say, carbon and oxygen, and there's a single bond here, so it's a pair of electrons. The electrons actually end up being closer to the oxygen than they do the carbon. It's still a single bond, like we see here, but the position of that pair of electrons is actually going to be closer to the oxygen. This is what I mean by not sharing electrons equally. One of the atoms will pull it closer, those pair of electrons closer than the other. And in this case, that's the oxygen. When we have this situation, when one of the atoms will pull the electrons closer to it than the other, we call that a polar covalent bond. Polar has unequal sharing. Now, why? That is based on what we call electronegativity. There's a trend on your periodic table. You've seen this already, but we'll go through it again. Electronegativity increases across the period, okay, and up a group. Fluorine is your most electronegative atom. We don't include the noble gases here because they don't form bonds. They have 8 valence electrons. Helium has 2, so they don't need to form any bonds. Okay, so electronegativity, each atom has its own electronegativity value. We're just going to look at trends. We're not going to focus so much on numbers. But what that is, electronegativity is the ability for an atom to attract the electrons. So again, if I look at the bond between carbon and oxygen, oxygen is more electronegative. That means it has the ability to pull the electrons closer to it than the carbon does. Okay, so it's still, again, in this case, if it's sharing one pair of electrons, it's still a single bond, but those electrons are closer to the oxygen because of its electronegativity value. Anytime we have a difference in electronegativity, we have a polar covalent bond. Well, that's not true. There's an area in terms of, we'll look at numbers, and here they are. If the difference in electronegativity is 0, then you have a non-polar covalent bond. Okay, so if the difference is 0, we call that pure covalent, and this is where you're talking about your diatomic molecules, like the chlorine. So 2 exactly the same atoms with a bond between them. They're going to share the electrons 100% equally. That's pure covalent, but it's also what we call a non-polar covalent bond. If the electronegativity difference is between 0.1 and 0.4, we have a non-polar covalent bond. So this is going to be all of your identical atoms, and then in addition, carbon-hydrogen. Every carbon-hydrogen bond falls in this realm, and that is going to be non-polar covalent. If the difference is between 0.5 and 1.9, so if you look back at that electronegativity chart and you're actually looking at numbers, that's when we're going to have polar covalent. So that's an unequal sharing of electrons. This is your carbon-oxygen bond. Okay. I'm going to simplify this. This is going to be 2 different nonmetals. We're going to assume that 2 different nonmetals are polar covalent unless we're talking about carbon-hydrogen. Carbon-hydrogen is nonpolar. If the electronegativity difference numerically is larger than or greater than 2, then we have an ionic bond. So these are your metals and your nonmetals coming together, like sodium chloride. Their difference in electronegativity will be greater, 2 or greater. But we know an ionic bond is metal and nonmetal, or it includes a polyatomic ion. Here's just showing this in a picture version. So this is like Cl2, this being Cl, or chlorine, Cl. They're sharing the electrons equally. This being like carbon and oxygen, unequal sharing. And then like sodium and chloride. Okay, we're actually going to come back to this at a different point, dipole moments, and same with this. Okay, so let's look. Do we have a non-polar covalent bond? So I'm going to write that here, non-polar. Okay, so we have a non-polar covalent bond, a polar covalent bond, or an ionic bond. All right, well here, strontium, is strontium a metal? It is. So I have a metal and a non-metal. So this one is going to be ionic. Nitrogen, chlorine, they're both non-metals. So I know it's going to be covalent. Is it polar covalent or non-polar covalent? It's polar covalent because they're two different non-metals. Nitrogen and oxygen, two different non-metals. So it's going to be polar covalent. Okay, let's do a couple more here. Iodine and iodine, both non-metals, but they're absolutely the same. So this is going to be non-polar covalent. So non-polar covalent. Cesium. Cesium, is that a metal? It is. So I have a metal. Bromine is a non-metal. So that is going to be ionic. Phosphorus and oxygen. So these are two different non-metals. So we have a polar covalent bond. So polar covalent. Okay, so now we're going to look at putting our structures together. And we're going to follow the Lewis theory. This has to do with valence electrons. And when we put our molecules together, the first thing we're going to do is count our valence electrons for each atom. And we're going to add them together. When we put our atoms together in terms of a molecule, we're going to look to fulfill that octet rule. So there's 8 electrons around each atom, with the exception to hydrogen and helium and boron. Okay, so let's look at the octet rule. This is a guideline for when we are putting our structures together. All right, we want to obey the octet rule. So that's 8 valence electrons around each atom. The reason being because that gives them a noble gas-like configuration. There are exceptions to the octet rule, and we will talk about them in more detail later. But the exceptions are sometimes our atoms can have more than 8 electrons around them, and we call that an expanded octet, so more than 8. This is only available for elements that are in the 3rd period or higher. The reason being is because they have the D subshell. And again, we'll go into that a little bit more later on. All right. When we write the skeletal structure for the molecule, so this is where we're figuring out what's our central atom, what's going to be in the middle. Like for water, for instance, if I have water, oxygen's in the middle. Why is it in the middle? So picking our middle atom. The less electronegative atom in the molecule is usually the central atom. That is not always the case. The one thing you need to remember about hydrogen is it's never going to be in the middle because hydrogen has 1 valence electron. It only needs 1. It's only going to form a single covalent bond. So it's going to be on the outskirts. Right? So hydrogens are always in that terminal position. So when we're drawing our Lewis structures, the first thing we're going to do is determine the total number of valence electrons. And rather than read through this, I'm just going to show you. Then we're going to distribute those valence electrons. We're going to start with the outer atoms and then focus on the central atom. And then if we don't have enough electrons, if we don't have 8 around our central atom, once we do that, then we're going to look at forming a multiple bond. Okay, so let's look at here. All right, so let's think about valence electrons. Carbon has 4. Oxygen has 6. So 6 times 2 is 12. Okay, so this molecule in particular has 16 valence electrons. Okay, so carbon has 1 carbon and 2 oxygens. One thing about structures is they're usually symmetrical, and carbon is almost always a central atom because because it can form so many bonds. Okay, so here's the rule. Here's how I would go about doing this. We've counted our valence electrons. I've picked my central atom. If carbon is available, it's probably going to be your central atom. And now I'm going to go ahead and fill my octets. I'm going to start with my outer atoms. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so I've used 16 of my 16 electrons. But let's see, I have a single bond here. This is the same thing. I'm going to write this here as this right now, so you can see that. Okay, so this is the same thing. All right, so I have 8 electrons around the oxygen, which is great. I want it. 8 electrons around here. But how many electrons do I have around carbon? I only have 4. And I need 8. But I don't have any more. I've used all 16. So this is where we're going to form a multiple bond. I can grab these two and just put them here. All right, I can grab these two, put them here. So what that leaves me with, these two are still here. And now I have 2 pairs of electrons in between each carbon and oxygen. Okay, so 2 pairs of electrons is equal to a double bond, but now let's see. I have 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around oxygen. So we're good. That works. So the structure of carbon dioxide is going to be, oops, sorry about that, 2 double bonds, and then there's still 2 lone pair of electrons on each oxygen. Okay. All right, so let's look here. Let's do carbon monoxide. All right, carbon has 4 valence electrons. Oxygen has 6. So in this structure, I have a total of 10. There's only one way we can do this, right? Oxygen and carbon. So let's say I do my 8 around oxygen. It's more electronegative. So, and then I have 2 more, so let's go ahead and put that there. So that's my 10 electrons. Right now I see a single bond in between carbon and oxygen, but carbon only has 4 electrons around it. Oxygen has 8. So now I need to move some. So if I move these, and let's say I move these, that gives me 3 pairs of electrons in between carbon and oxygen. But now I have 8 electrons around the oxygen and 8 electrons around the carbon. So that gives me this structure. Let me write that again. I have a triple bond here. And I have 8 electrons around each atom. So that would be my Lewis structure. All right, we're going to do a couple more. I'm going to run through these fairly quickly. So nitrogen has 5 valence electrons. Hydrogen has 1, but I have 3 of them, so I have 3. Okay, so I have 8 valence electrons to work with here. I know my central atom is going to be nitrogen because hydrogen is always terminal. So I'm going to write that. I'm going to go ahead and put 8 valence, or actually we'll start with our outer ones. Hydrogen only needs 2, so 2 around each hydrogen. It's going to make that single bond. So I've used 6 out of the 8. Hydrogens are all fine, they have 2. So I'm going to put my remaining electrons, I have 2 left on the central atom. And so that gives me the structure for ammonia. I have 3 single bonds, hydrogen is satisfied, so is nitrogen, because with that lone pair, it has 8 around it. Okay, let's look here. Hydrogen has 1 valence electrons, but I have 2, so I have 2. Carbon has 4, and oxygen has 6. So I have a total of 6 plus 4 is 10, plus 2 is 12. Okay. Picking my central atom, I'm always going to choose carbon when I can. So hydrogen's here. Okay. I want to fill the valence shell of my outer electron, or my outer atoms. So for hydrogen, how many is that? It's 2. So remember, hydrogen only makes a single bond. So 2, 4. So I still have 8 left. Now I'm going to fill it on this one. So I'll put those 8. 1, 2, 3, 6, 7, 8. Okay. Now we check our central atom. Our central atom only has 6. It needs 8, which means I need to make a multiple bond because I don't have any more. So let's take these and put them here. Again, it doesn't matter which one you take. So then I would have this. So I have 2 pairs of electrons. So now each hydrogen has 2, which it wants. Okay. And now the carbon has 8 around it, and so does the oxygen. So the carbon-oxygen is double bonded. The carbon-hydrogens are single bonded. Okay. Let's look here. Now we have an ion. So this is a little different, although we're not going to do it any differently. All right, so nitrogen has, 5 valence electrons. Hydrogen has 1. I have 4 of them, so there's 4. So that's 9. And then I have a +1 charge. So that means I'm lacking an electron. So we got to subtract 1. So I have a total of 8 valence electrons. My center is going to be the nitrogen. I've got 4 hydrogens around it. Okay, each hydrogen is going to have 2 to make that single bond. Right, so we now use all 8. Is the nitrogen satisfied? It is. 2, 4, 6, 8. So we have, when we have an ion like this, so I'm going to draw it with the bond rather than just the pair of electrons. We're going to put that in a bracket because it's an ion and put the charge outside of it. So that would be the structure for the ammonium ion. Okay, let's do one more here. This is the hypochlorite ion. So chlorine has 7 valence electrons. Oxygen has 6. The negative charge is adding an electron. It's -1. So I have 7 plus 6 is 13, plus 1 is 14. So this structure has 14 valence electrons. You can only put this together one way. So let's go ahead and fulfill. We know chlorine has 7 valence electrons. It usually needs 1 to make 1 bond. So let's fill the octet here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we filled the octet of both. We used all 14 electrons, and both of them have 8 electrons around it. So that this one actually ends up being pretty simple. So there's a single bond between them. And then they both have 3 pairs of electrons. And then because it's an ion, we're going to put it in brackets and show that charge, -1. You don't have to write the 1, just the negative. Okay, so that's our introduction to drawing Lewis structures.